1 second. Okay.
Okay, so this is a talk about parsing synchronous context-free grammars. And here's what a synchronous context-free grammar looks like. So it's like a context-free grammar. You have in context-free grammar, you have a rule of non-terminal goes to a right-hand side with two non-terminals on the right-hand side. And synchronous context-free grammar means it generates Chinese and English at the same time. So every rule has two right-hand sides, and they can be terminals like Chinese terminals and English terminals, or they can be non-terminals like this. And this means that you have the non-terminals come in one order in English and some other order in Chinese. So you can have reordering between one language and the other. You have to have the same set of non-terminals on both sides. And you have these indices that tell you this one Chinese goes with this one English. And so this is kind of the way that all statistical machine translation systems work these days. So they're kind of based on the synchronous context-free grammar as the translation models. And the grammars are extracted from corpora, so you have documents in Chinese and English, and you extract rules left alone on the last line, learning grammar. And so parsing with the synchronous context-free grammar means parsing two strings at the same time. So that could be in the context of machine translation that you have these two sentences and you're trying to figure out which Chinese words go with which English words. So that's word alignment. So parsing with synchronous context-free grammars can be used in that context, and also to learn probabilities for the rules for your translation model. So in machine translation, typically the rules only have two non-terminals on the right-hand side. So binary grammars. It's also called inversion transduction grammar. So ITG is inversion transduction grammar. And you can parse in time n to the 6, where n is the sentence length. It seems to be that in real machine translation, you don't need more than two non-terminals on the right-hand side. If you do have more than two non-terminals on the right-hand side, you can't always reduce it down to 2. So we'll see examples of that. That means that rules of length R are stronger than rules of length R -1. And this was shown back in the early days when they developed this formalism. They were thinking more about compilers rather than Chinese and English, but it's the same thing. And this talk is going to be about what you do with these long rules. So how you do parsing with rules where the number of non-terminals on the right-hand side is very long. And we don't really need this for machine translation because we think 2 is enough. And maybe in the future, we'll use more than 2. But even if we don't, I think this is important just because synchronous context-free grammar is such a basic formalism. So it's kind of a natural extension to context-free grammar. It goes all the way back to the 60s. And so we should know what is the complexity of parsing and how to do it. Okay. So I'm going to give some background on parsing. So here's how you parse a context-free grammar. So you know the CYK algorithm. This is my picture of the CYK algorithm. So if you have a rule A goes to BC, then when you parse that rule, what the algorithm is doing is it's combining two spans. It's already found some span in the string that represents B, that makes a B, some span in the string that represents a C, and it puts them together to produce a span that represents A. And so this picture means that we've found these two spans and they have to be adjacent to each other. So this is a position in the string, a position in the string, the end of the B has to be the same as the beginning of the C. And the beginning and end of the A come from the beginning of the B and end of the C. So we glue two substrings together to make a longer substring. And we do the same thing in fancier formalism. So if you know tree adjoining grammar, in tree adjoining grammar, a non-terminal can generate more than one substring of the entire string. So this would be, you parse tree adjoining grammar, you found something that generates two pieces of the string, combine it with something else that generated two pieces of the string, and they have to match up in this nested way. So the two C's are inside the two B's, and they're adjacent here and adjacent here, and you combine them together to get the A on the left-hand side of the rule, and it also has two substrings, two spans that you get by putting B and C together. So that's just if you like tree adjoining grammar. Let's go back to synchronous grammars. So inversion transduction grammar, this is synchronous context-free grammar with two non-terminals on the right-hand side. So here's the two non-terminals on the right-hand side, and you're combining them to make the non-terminal on the left-hand side. And so now you're parsing English and Chinese. So think of taking the English string and gluing it together with the Chinese string to make one long string that you're parsing. And you've already found a B, and it covers something in English and something in Chinese. So you cover something in English, something in Chinese, and you combine those together to make an A, which covers something in English and something in Chinese. And this pattern means that B was before C in English, but B was after C in Chinese. So there's a switch in the order. And in inversion transduction grammar, there's two patterns that you can have. Either they were in the opposite order in the two languages, or they were in the same order in the two languages. Okay, so this is what parsing ITG would look like. In general, synchronous context-free grammar, you can have more than two non-terminals on the right-hand side. So here you have four. And so you go B, C, D, E in English. But in Chinese, if you go left to right through Chinese, it's C, E, B, D. And this is an example of one of those rules where you have something with four symbols and there's no way to do the same thing with only two symbols. And it's because there's some complicated pattern here. So there's no way you grab the B and the C, the first two things over here. B and C are not adjacent in Chinese, so that doesn't make a valid rule in Chinese. Okay, so we have these pictures. How can we analyze them? One way to analyze them is fan out. Fan out means the number of spans that the non-terminal generates in the string. And so if the fan out is 1, that's context-free grammar. So it's kind of the normal situation. One symbol generates one substring. Tree adjoining grammar, we have these two spans, so that's fan out 2. Inversion transduction grammar was also 2, so each row here had 2 spans in it, each symbol had 2 spans. The general synchronous context-free grammar is also fan out 2, so it's every symbol has 1 span in English, 1 span in Chinese, so it has 2 spans. So it's not different from ITG yet. Fan out is 5. Fan out of a grammar is the maximum fan out of any of the non-terminals in the grammar. And that's one way to break it down, and the other way is the rank. Rank is the number of symbols on the right-hand side of the rule. So 2, 2, 2, here we have 4. And rank is a function of, it's not a function of the non-terminal, it's a function of the production. It's how they combine in one rule. And so the rank of the grammar is the maximum rank of any production in the grammar. Okay. So we want to parse efficiently. And when you parse, if you want to parse a context-free grammar efficiently, the first thing you do is transform it into Chomsky normal form. So Chomsky normal form means rank 2, 2 symbols on the right-hand side of each rule. And this is what taking a rule and converting it into Chomsky normal form looks like in terms of these pictures. So you had a context-free grammar rule with 4 non-terminals on the right-hand side. You can break it down into steps. So the first step is you combine the B and the C, the first 2 symbols from the rule, and you make some intermediate results. You make some new non-terminal grammar. When you're parsing, you make some intermediate entry in your table that says I found B and C so far, found X so far. And you keep going, you combine what you found so far with the next non-terminal from the original rule, the next non-terminal from the original rule, and then you're done. Okay, so we've simplified the parsing because here we had to find this point in the string, 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 this point in the string. Here we just have 1, 2, 3 points in the string in each step. And that's why parsing context-free grammar is n cubed. So at each step you have 1, 2, 3 variables that point to positions in the string, and you're considering all combinations of those. Okay, so if we want to do the same thing for synchronous context-free grammar, it's more complicated. So here we have a rule with rank 4, some complex reordering on the Chinese side. If we do the same thing, we take the first 2 symbols in English. We can make an intermediate result in English. And we can take the spans that they cover in Chinese, but they don't touch each other. So we're making some intermediate result that has 1 span in English and 2 spans in Chinese. Okay, so that means that we're doing some kind of parsing strategy to reduce the rank because we only have 2 symbols in this step, but we increase the fan out. So everything was fan out 2 before, and now this new thing that we're making is fan out 3. So there's some cost, there's some trade-off. So if you're interested in the time complexity of the algorithm, that's the time complexity depends on the total number of indices into the string. So for normal context-free grammar, let's give it time 1, 2, 3 indices into the string. Here's the, this could be either ITG or the tag picture. They're both end in 6 because we have 1, 2, 3, 1, 2, 3. Okay, so that's like saying you're doing, for ITG, you're doing kind of like normal context-free grammar parsing in English, which is n cubed times context-free grammar parsing in Chinese, which is n cubed times n to the 6th. And the general formula would be there's some parsing complexity of a production P, and the time for parsing is the length of the sentence and to some exponent. That exponent depends on the rule production. And that exponent, you can get it from the fan out. It's the sum of the fan out of the left-hand side and the fan out of all the symbols on the right-hand side of the rule. And so for English, or for CFG, you have 1 plus 1 plus 1. You have 2 plus 2 plus 2. And it makes sense because the parsing complexity is the total number of indices into the string. So it's the total number of endpoints of these spans. And so every span has 2 endpoints. Okay, so that would be 2 times the total fan. But every endpoint is used twice in the rule. So either it's used, these 2 non-terminals meet, so they have the same endpoint, so that's it's used twice here, or it's not. Doesn't combine with somebody else, but then it's in the new symbol that you're making, so it's used twice here. Okay. So it's 2 times the total fan out divided by 2, so it's the total fan out. That's the exponent. And so this is the equation we had on the last slide. For grammar, generally you want to, you're interested in what's the worst rule. So the parsing complexity for the grammar would be the maximum of the individual rules. And you can come up with some bound, some relation to fan out. So just from this sum, this has to, the complexity for parsing is no worse than the worst fan out times the total number of symbols involved in each rule. Okay. So the rank plus 1 symbols on the left-hand side, 1 symbol on the left-hand side, times the maximum fan out of all of those symbols. So there's some relationship between the fan out of a grammar and the parsing complexity of a grammar, but not exactly the same. Okay, so for synchronous context-free grammar, what will that exponent look like? What will that parsing complexity look like? It depends on the rule, depends on the pattern, the permutation between the English and the Chinese side. So here are some bounds on it, though. So you can always do at least as well as the number. R is the number of symbols on the right-hand side, the rank plus 4. You can do that by just going left to right through English. So that's like into the 3 in English. And then at the worst, you would have another n plus or R. So if you have R symbols, you have R plus 1 indices in Chinese, all possible indices in Chinese. 3 in English, R plus 1 in Chinese. And that's if you just do something stupid. So just go left to right through English. That's the simplest possible thing. We can do smarter things than that. So that's what this talk is about, finding better strategies. You can find better strategies. There is some optimal strategy, and this is found on how good the optimal strategy can be. So if you have very complicated rules, and if they get longer and longer, so R is the rank, the number of symbols on the right-hand side of the rule, then this parsing complexity is growing linearly with that rank. So we know from previous work that nothing we do can push this all the way down to a constant. It still depends on the rank. But we want to push it down as far as we can, especially because this is in the exponent. So, questions? Okay, so this paper is about finding the best parsing strategy for a synchronous context-free grammar rule. It's about linear strategies. So linear means you add one non-terminal at a time. Okay, so like in the examples we've had so far, you're making partial results and you add one non-terminal at a time for the partial result. And basically the result is that it's NP complete to do that. So, so doing the parsing is NP complete, but it's also NP complete to figure out the best way of doing the parsing. And that's true whether you're interested in finding the best parsing strategy in terms of fan out, which is the space complexity of parsing, like how many entries you need to store in your dynamic programming table, or the time complexity, which is the, as we said, is related to the fan out. So minimizing fan out, minimizing parsing complexity are not exactly the same thing. Okay. Okay, so let me show you another example. This is a longer rule, so 6 non-terminals on the right-hand side, and this is kind of to illustrate why it makes a difference what your parsing strategy is. So you have A, B, C, D, E, F in English, and then some other order in Chinese. This is what happens if you go left to right through English. So let's say the first step. We picked the A and the B with English, they were adjacent. They weren't adjacent in Chinese. At the end of this first step, we have n out of 3, 1, 2, 3. And the complexity of this step was 7. 1, 2, 3, 4, 5, 6, 7. In the next step, we're going to add the next thing in English. And the next thing, and that corresponded to something in Chinese that wasn't adjacent to either of the two things we've done so far. So now it's getting worse. We have fan out 4. 1, 2, 3, 4. The complexity of this step was n to the 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And we keep going, add the next thing in English, and now finally you see something in Chinese that plugs this hole, so that's good. So now we're back down to 2 spans in Chinese. So we have something with total fan out 3, and the complexity of this step was also n to the 9. Okay. So this is one parsing strategy for this rule, and it's not the best parsing strategy. Basically, the reason for that is that we created these 2 gaps here, so that's bad. So it turns out that if you look at the entire rule, and if you kind of start in the center, so maybe if you grab these 2 in Chinese, they're adjacent in Chinese, they make one gap between them in English, and then you can plug that gap in English and open up one gap in Chinese, and just generally do better not ever have 2 gaps in there at the same time. Okay, so so we want to find the better parsing strategy, and the parsing strategy is some order in which you add the non-terminals. So it's some permutation of the non-terminals. That's what we're looking for. Okay. Okay, so here is a way of representing this problem with a graph. So define what we call permutation multigraph. And for this rule, you can make this permutation multigraph. And the graph has a vertex for each of the non-terminals on the right-hand side of the rule, A, B, C, D, E, F. And it has a red edge if the 2 non-terminals are adjacent in English, so A, B, C, D, E, F. There's a green edge if they're adjacent in Chinese, so F, A, and A, D, and then D, B, E, 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 C. Okay, so those are the edges in Chinese. And so basically it's another way of representing the permutation in the rule. Okay, so if you put the vertices in the English order, then the green edges represent the permutation of the reordering in Chinese. So there's an edge between 2 vertices if they share a boundary, either in English or Chinese. And those boundaries are what matter in terms of the parsing complexity. So here's the first step, again, from that parsing strategy that we had earlier. And parsing strategy that we had earlier went A, B, C, D, E, F. So it combined non-terminals in that order. So if you imagine that parsing strategy going through this graph, it's kind of marching through this graph, adding one non-terminal at a time. What you have to the left is everything that you've collected so far. And the edges tell you which boundaries are active at this step in the parsing. So for example, very first step, you combine A and B. So you combine A and B, and then you have this stuff so far. You have these edges crossing from what you have so far to the stuff you're still looking for. And this edge is the edge between B and C, so it's this edge. This edge was the edge between A and B, and we're done with it. We don't need it anymore, so it's not crossing this boundary. We can forget about it. And then these green edges, okay, we've combined A and B, so we have the 2 boundaries for A Chinese, that's these 2 edges, 2 boundaries for B and Chinese, that's these 2 edges. And so if you look at a one step in the graph, the number of edges crossing that step is the number of edges, number of boundaries that exist in this new thing that you've built. Well, except we didn't have an edge for this. This is special because it's at the very beginning of the rule, so it doesn't count. And if we just count the edges that we have here, so we have 5 edges crossing this point. And 1, you get 6. Divide by 2, you get the fan out of the thing that we built. So it has 3 spans, 6 boundaries. Okay. So the number of edges crossing a gap in this graph is the fan out. And the parsing complexity, what is it? So what does it have to do with this graph? Parsing complexity is basically it's the total number of indices involved in the step. So that's like the number of boundaries you have here, or the number of edges crossing here, plus the new edges that you create. So it's not exactly the same thing, but it's also something that you can read off this graph pretty easily. Okay. So what I just described is called Cutwits in graph theory. So number of edges that cross a boundary in a graph. So this is the width of a graph. So you have a graph, you have some ordering of its vertices. So mu is A, B, C, D, E, F. And then you have a position in that ordering, that's I. So I would be I equals 3. And we cut it here. And the width is how many edges cross that point. So for all the edges in the graph, how many have one boundary to the left of I and one boundary to the right of I? One vertex to the left of I, one vertex to the right of I. Okay, so that's the width of a graph and a linear layout at a specific position. And it's the same thing as fan out, basically. And the cut width of a graph is you're looking for the widest point. So as you move left to right, where is it the widest? And you want to keep that as low as possible. You get to choose the ordering. So if you can choose any linear ordering for the vertices, what is the ordering that keeps the width the lowest? And choosing a linear ordering of the vertices, so this min over nu, that's finding our parsing strategy. So it's figuring out what order you want to combine them on. So the cut width of so we made this graph. The cut width of the graph is the best fan out that we can achieve. And cut width is an NP-complete problem, kind of a classical NP-complete problem. So minimizing the fan out is NP-complete, except not quite, because these are special graphs. Okay, so it's minimizing, it's finding the cut width of this special class of graph that I defined that has one green path and one red path. So we need to show that finding the cut widths of these graphs, these permutation multigraphs, is NP-complete. So we need to do some reduction where we take an NP-complete problem, convert it into a permutation multigraph, and finding that cut width solves the original problem. And for a while we couldn't figure out how to do that because this is all about permutation. So permutation multigraph it is a permutation, and somehow how do you turn set cover into a permutation? How do you encode some NP-complete problem in one permutation? So here's how you do it. So the source problem for the reduction is minimum bisection width. Minimum bisection width is you're given a graph, you have to cut it into 2 pieces. You have to have the same number of vertices in each of the 2 pieces, and you want to have as few as possible edges crossing between the 2 pieces. So you're given, to make it a decision problem, you're given a graph in integer k, you want to find 2 divisions of the set of vertices with equal size, no more than 8 edges crossing from one partition to the other. So that's our source problem, and we're going to turn it into a permutation multigraph. And so that's how the reduction works. So you give me a graph and K, a bisection width. We're going to make a permutation multigraph that's G prime. There's going to be some number K prime that comes from K. And these two problems, we want to make these two problems equivalent. So that means that if you can cut G in half with no more than K edges crossing, then there must be some way of arranging the vertices in G prime with Cutwits K prime. And vice versa, if there exists some way of arranging the vertices of G prime with low Cutwits, that gives you a way of cutting the graph into two pieces. Okay, so we're going to build a graph. So we're going to take G and build G prime. And G prime is built out of these grids. Okay, so here's a picture of the grid gadget. We're going to make one of these for each vertex in the original graph. And there's also a big one extra gadget that's made out of 3 grids in this kind of L pattern, and we call it L, 3 grids L, M, and R. And everything fits together in this pattern. So there's going to be one grid for each vertex in the original graph. So the original graph, let's say, was just one chain with 4 vertices in it. So it had 4 vertices, 1, 2, 3, 4 grids, and for each edge in the original graph, there's some connection, 2 edges connecting G1 to G2, G2 to G3, G3 to G4. And then there's also one giant grid that's kind of the heart of the whole thing, and it has a big bundle of edges going to each of the G's. So N is the number of vertices in the original graph. We have 2 edges for each edge in the original graph, and we have 4 n squared edges connecting this heart thing to each grid. So what does this have to do with bisecting the original graph? So build this giant graph, and now suppose that there's some way of arranging it in a line with low widths. Okay? So basically what we proved is that if that's possible, then that linear arrangement has to look like this, basically. So if you go left to right in your linear arrangement, you have all the vertices from one gadget, all the vertices from the next gadget, all the vertices from the center, and so on. And it should make sense because, first of all, each grid should have lots of edges inside them, so they want to stay together. So if you were to break a grid into 2 pieces, there'd be lots of edges flowing across those 2 pieces, and that would not be good for your code. So the grids stay together, and the position of the grids is going to correspond to the bisection of the original graph. So all the people to the left of the center are in one half of the bisection, and everybody to the right is in the other half. And we need to enforce that there are half on each side. So there's n/2 grids on each side of this center thing. And that's what these thick bundles of edges are for. So the critical point for the width of the whole thing is here. And that's because this is a very big grid. And the width of this point grows every time you root 4 to the n squared edges over it. And if you put more than half of them on this side, you're going to have too many edges here. And if you put more than half of them on this side, you're going to have too many edges here. So you have to have exactly half on both sides. So that's how you get the bisection of the original graph. And then the critical point is here. And so it also includes the edges that cross from one half of the bisection to the other half. So the edges from the original graph. So that's how width of this whole thing corresponds to the bisection width of the original graph. Okay, so that's the that's the main idea of the reduction. And I'll tell you a little bit more what the graph looks like, but this is really the main idea of the reduction. So any questions? Yeah.
Is there any is there a problem if the graph has like what would you do with an odd number of nodes?
We actually assume, well, you just can't have that. Okay. And in fact, we assume that the original graph, each vertex has exactly 3 edges, and bisection width is still NP-complete under that condition.
Oh.
So, yeah, as long as the original problem is still NP-complete.
Okay.
Balanced, again, the bisection is it similar to the balanced?
I don't know what the balance cut problem is. It might be the same thing.
Considering they want to cut it in a way that each of the clusters have same number of data points, but they do not cut any edges.
It sounds like exactly the same thing. Okay, so this is how you build the graph, and the graph has to be a permutation multigraph with a red path and a green path. So I haven't showed you how do you make it out of a red path and a green path. And so there's one red path, and it does all the rows, and the green path does all the columns. Okay, so here's what the red path does. This is the center of the whole thing. This is the grid for one vertex of the original graph. So the red path zigs back and forth through all the rows, covers all the rows, the edges and the rows of the grid. And when it goes along the top here, it visits each of these grids one after the other. I've just shown one here and goes through its rows. Okay, so just hits all of the rows, and the red path doesn't have anything to do, doesn't depend at all on the structure of the original graph. The green path does all of the columns. So it goes up and down the columns of the big grid at the heart, and it goes up and down the columns of the individual grid gadgets. And we need this thick bundle of 4 n² edges, so the green path goes back and forth up one column and down until you get 4 n² edges. And then it also goes off to the other grids. If there was an edge here in the original graph from I to J, then it goes up through I, off to J, comes back. Okay. And this is the picture of the same thing. So it goes up to I, goes through J, up and down, comes back, down, and back to the center. And this is just some more detail of how you get those n4 n² edges between the center and graph gadget I. And this is bigger than 4 n². You go up and down these columns until, so everything's connected in the first block of columns. And you have another block of columns for the green edges that correspond to the original edges. So that's inside here. And then you have a one more block where you just go through staying in this gadget. You come in once, staying and go back. Okay. And that's it. So yeah, so just to review. So you have the green path, the red path. You build this whole thing, and if you can put this in some linear order with cut with no bigger than some k prime, with no more than k edges crossing here, you can bisect the original g with no more than k edges crossing. And so that's it. So it's NP complete. It's NP complete to optimize the fan out The fan out was the cut width. Parsing complexity was not exactly the same thing as the cut width, but it was almost the same thing. So you can extend this to show that parsing complexity is also NP complete. And this is about parsing strategies for synchronous context-free grammar. So parsing with a synchronous context-free grammar means parsing English and Chinese at the same time. So what about when you're doing the translation? So you have the Chinese string coming in. There is no English string. So you're just parsing the Chinese. So that's easier. Actually, you can do it in N-cubed because you just forget the English part of the grammar and press with the Chinese side. But in real machine translation systems, you have a language model which does depend on the English side as you're building it. You want to have a score for n-grams on the English side. And it turns out that if you include the term for the n-gram language model, the complexity of the big O is the same for doing the translation and for doing the synchronous parsing. So that everything that I said, this proof also applies to the situation we're actually doing the translation. That's it.
So I was wondering, are the non-terminals we're talking about here, so for linguistically viable non-terminals, are they just chunks of whatever is found?
Well, they can, you can do it either way. So, one thing that people do is they take the English and the Chinese strings, parse the English string with an automatic parser, and then do some kind of extraction process on the parsed string. So then you get out terminals that correspond to nodes in your parse trees, and you can actually have verb phrases and noun phrases and so on. But you can also do it the other way, where it's just chunks.
So if you do it the first way, what I was thinking was, like in HPSG, you, I think that's one of the grammar systems anyway, maybe others, you can divide the grammar into immediate dominance and linear precedence. And so a thought that I had when you were talking about how with the scrambling on the Chinese side increases your complexity, I was thinking, wow, if only we knew the linear precedence rules for both languages, then we could.
Yeah.
So can one maybe learn immediate dominance and linear precedence kind of in a separate way, and then everything's linear?
Well,
or cubic.
No, that would not make everything cubic, because parsing IDLP grammars is also NP complete for basically the same reasons. I mean, if you have very big rules, well, I guess if your IDLP constraints correspond to one of the grammars that I showed you, then it has to be complete if they do the same thing.
Mm-hmm.
And parsing IDLP in one language is also NP complete if you're allowed to make the rules arbitrarily long, arbitrarily non-rules. So then it's like a set cover thing. So if you have no linear precedence constraints, you can recognize things in any order. So it's like unordered context-free grammar parsing, and you can do set cover.
So if we can find them to a parsing strategy, even then that would be exponential, like this strategy.
So it's exponential in the length of the rule, but polynomial in the length of the string that you're parsing. So at least something is polynomial.
I was wondering, will there be any impractical like parsing will it be used to find a good strategy, like finding an approximation of bisection path?
Yeah, I think that I mean, I think it makes sense to say that even if you don't have the optimal strategy, if you can find something good, then that's good. And I haven't really thought about, I don't know if there are approximation algorithms for bisection cut, but you can do some kind of best first search over these permutations and get something reasonable. That way.
Just on one like similar to spectral clustering where they do a relaxation of the bisection by saying the variables have to be 0 and 1.
Okay, okay. Okay. Okay, but the rules that we make from instances of bisection cut are strange SCFG rules. They're not general SCFG rules. They're these crazy grids. So I'm not sure if you can. Okay, thank you.
Thank you.
Thank you.